Okay, so today we're going to be continuing our unit on probability and statistics with 6.2 permutations. So our learning target is I can count the number of ways a permutation can happen. In other words, I can find the total number of outcomes for a permutation. I also know the meaning of a factorial and can evaluate one. So what is a factorial? A factorial is a new math operation we're learning today, notated with an exclamation point. It means to multiply a number by every whole number from there down to 1. So the example given is 5 factorial is equal to 5 times 4 times 3 times 2 times 1. We can actually put factorial into our calculator, which you're going to need for today's lesson and for the Delta Math homework. So if you push 5 in your calculator, and then you push the PRB button, then factorial is going to be the third option that pops up. So you can either scroll down and click enter on the third option, or you can just push 3 from there. Then it should say 5 factorial in your calculator screen, and if you push enter again, it should give you 120 as your answer. If you got 120, then you did it right. Okay, so there is one important case or special case that we want to talk about here, and that's 0 factorial. 0 factorial doesn't follow the definition given, but we want to remember that 0 factorial is 1. It's a good thing to keep in the back of your mind, but if you do forget it, you can always put 0 factorial in the calculator and it will give you 1 as your answer. So some of this might look a little familiar. Last class we talked about dependent events. And like in this example down below, choosing a president, vice president, and secretary out of a class of 25, we multiplied 25, 24, and 23 together and got our answer. Well, that right there is the beginning of a factorial. It's not a complete factorial, but it is the beginning of a factorial. So let's look at some more examples of factorials and see if we can start to get the hang of this. So in our calculator, if you push 1 factorial, you should get 1 as your answer. And that makes sense because we're starting at 1 and we're multiplying all the way down to 1. Well, there's nothing more to multiply it by, so we get 1 as our answer. Then, if we do 6 factorial, what's actually happening here is 6 times 5 times 4 times 3 times 2, then times 1. But 6 factorial is a whole lot faster than typing in all those numbers in our calculator. Either way you do it, though, you'll get 720 as your answer. Now looking at C, we have 0 factorial. Well, that right there is our special case. So we already know that 0 factorial is 1. Now for 11 factorial, we can simply put 11 factorial in the calculator, or we can do 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But 11 factorial is a whole lot simpler to put in the calculator, and there's less of a chance that you'll misclick a number or an error will occur. If we put 11 factorial, or if we type all that in, we'll get 39,916,800 as our answer. Now I wrote all that out for 11 factorial, but for 22 factorial, it's an even larger number and it takes even longer to write it out. In fact, it's so large that our calculator probably doesn't even give us the right answer. It gives us it in scientific notation, which doesn't really help us anyways. So for these two, we're just going to leave as is because there's such large numbers that that's the simplest way to write it. So moving on, we have permutations. Permutations are the number of ways something can happen, or the total number of outcomes, when the order of items or specific titles matter. That sentence right there is super important. In a permutation, order matters. That's important to remember because as we go further in this unit, we'll find another tool where order doesn't matter. But it's important to remember permutations, order matters. Some examples of permutations would be choosing a president, vice president, and secretary, because if different people held different titles, it would be a different presidency. Another example is running a race, and getting the first, second, and third place matters, because if not, the gold medalist would get a different reward, or we'd have a different podium. Same thing with a password. If your password is 1234, you can't put in 4321 because the order of every digit you put in matters. Okay? So, let's do some examples of factorials here. Looking at example 1, how many different seating charts could be made of a class of 30 students if there are 30 desks? Well, we have 30 students and we have 30 desks, so in our calculator we're just going to put in 30 factorial. When you put 30 factorial into your calculator, you get such a large number that it doesn't even make sense. You might even get an error because it's way too big of a number. Well, I've written down what 30 factorial is, and it's this number right here. It's way too large. It almost means nothing to us because there's so many digits. So you see, this is why we have the factorial, because 30 factorial is a whole lot more simple than writing all that down. Okay? So looking at number 2, how many ways could 5 racers earn medals if everyone gets a medal? Well, we've got 5 racers and everyone's getting a medal, so we can do 5 factorial. And if we do 5 factorial in our calculator, we get 120 as our answer. Pretty simple, right? Okay, so number 3, how many ways could the letters in the word design be arranged? Okay, well, if we look at design, we've got 6 different letters. So I've got 6 letters, and I want to know how many how many ways they can be arranged. So 6 factorial, and that gives me 720. Looking at number 4, how many different ways could 8 posters be hung in a row on a wall? Well, I've got 8 different posters, and I want to know how many ways they can be arranged. That's 8 factorial. If I type that in my calculator, I get 40,320. All right. Number 5, how many ways could 7 people stand in a line? Well, just like the last examples, we've got 7 people. We'll do 7 factorial, and that gives us 5,040 as our answer. Okay, now this one's a bit different. How many unique ways could 7 people stand in a circle? Okay. Now, if 7 people are in a circle, you can move them around a whole lot and make a lot of different unique ways, just like in the last one. But if you think about a circle and you have 7 different people in it, like here, we can take our circle and we can rotate it a little bit. Now, they're in a different spot for sure, but they're not in a different order. The black is still next to the purple, and the purple is still next to the orange. And I can do that again and again. I can rotate it all the way around. It's still the same order, just in a different rotation. So when we have a circle, we can do this 2 ways. The first way we can do it is we've got 7 people, so we've got 7 factorial, just like above. But we have to count for, there are 7 different ways I can turn this circle that I get the exact same order. So if I do 7 factorial divided by 7, I'll get 720 as my answer. I can also do this by taking 7 and minusing 1 of my full circles, and that'll give me 6 factorial, which will also give me 720. Whichever one makes more sense to you, that's perfectly fine, as long as we remember that because it's a circle, it's got that special case. Alrighty, looking at number 7, how many unique ways could the letters of the word cheese be arranged? Okay, so this one's kind of like the one we did above with the word design. The difference is the word cheese repeats E 3 times. So I'm going to start this one just like I always started the other one. I've got 6 letters in the word cheese. But for this one, I've got 1 letter that repeats 3 times, so I'll divide it by 3 factorial. And when I put that in my calculator, I get 720 over 6, or 120 unique ways. Okay, a kind of similar problem to the one before with the word Arkansas. This time I've got 2 letters that are repeating. Both the A and the S repeat. So I'll start it just like I started my other 2. Count up my letters. I've got 8 letters, so I'll put 8 factorial. Okay, now look at each of the repeats individually. The A repeats 3 times, so I'll put 3 factorial down here. And then my S repeats 2 times, so I'll put 2 factorial. And what we're doing is we're multiplying these together. So in your calculator, if you put that in, you'll get 3,360 as your answer. So when we have multiple repeats, we count up how many each letter repeats, and we multiply those factorials by each other. Okay, so here's a summary of those rules we just went over. A permutation of n distinguishable or different items is n factorial. Just the basic factorial. But what this says is factorial is a subset of permutation as a whole. So we'll get more into permutation in just a minute, but factorial is a subset of permutation. Okay, now the second one, permutation of n items, which p are alike and q are alike, is n factorial divided by p factorial times q factorial. That's like our Arkansas example. Okay, and then the last one, a circular permutation of n events, is n factorial divided by n. Just like our 7 people, we did 7 factorial divided by 7. Okay. So what if we want to arrange items, but we don't want to arrange all the items? What if we only wanted to choose the first, second, and third place out of 10 racers? Or what if we only wanted to hang 4 of the 9 available posters, or form 3-letter words from our 8-letter word? Well, we've done that already, like in the examples we've done earlier, when we did 25 times 24 times 23 to find out how many different presidencies we could make in our class of 25. But what if the group is so large, like what if we're trying to assign placings for 100 scholarship winners out of 1,000 applicants? Well, then you have to multiply 100 different numbers together, and that would take way too long. So when it comes to this, we're going to use a permutation. Now there's also a permutation button in your calculator. So for this, we need an N and an R. So we're arranging R items from a group of N items. So basically, if we've got a group of 10 people, that would be our N, and we're trying to choose 3 of them, that would be our R. So in your calculator, let's go to example A down here. If we have 5 things and we're trying to choose 2 of them where order matters, we're going to put a 5 in our calculator. Then we're going to push the PRB button again. And the permutation is the first one, so you can push 1 or you can just push enter. So it should say 5 NPR, and then you'll put a 2 in. And if you put that in correctly, you should get 20 as your answer. So 5 NPR2 is 20. Okay. Now if we do the same thing and we put 83 NPR0, we're going to get 1 as our answer. That's because of the special case we talked about earlier. We're choosing 0 things. And if we're choosing 0, it's really 0 factorial, which is 1. Okay. Now looking at 22P22. If we put that in our calculator, we're going to get a large number. But if you also put 22 factorial in your calculator, you'll get the exact same number. So what a factorial really is a permutation where you have 22 things and you're choosing 22 of them. So if we have the same number right here, it's really just 22 factorial. Either way, you'll get the correct answer, but if you want a little shortcut, that's one way you can tell. Okay, now if we put 9 NPR 4, we'll get 3,024 as our answer. Okay, now 15 NPR 1, that will actually give us 15. And this kind of makes sense if we think about it, because if we have 15 cookies or 15 books, for example, and we want to choose one of the books, then we only have 15 that we can choose from. So anytime it's 15 NPR 1, the answer will always just be your first number. Alrighty, let's do a couple more examples. So it says Joe is trying to find as many 3-letter words as he can using the letters in the word Monday. How many possible arrangements could he try? Well, we've got Monday, which has 6 letters, and order matters here, so 6 NPR 3 is what we'll put in our calculator. That'll give us 120 as our answer. Okay, so a committee of 50 people want to select a president, a vice president, a treasurer, and a secretary from its membership. Anyone can hold any position, but no one is allowed to hold more than one position. The permutation NPR can be used to find how many different presidencies the committees could have. What would be an appropriate value for N and R? Well, I've got 50 people, and I'm choosing a president, a vice president, a treasury, and a secretary. So, N is always our bigger number, our number that we're pulling from. So 50 could be our N. And 4 could be our R, because we have 4 different positions. A president, a vice president, a treasurer, and a secretary. So if we were going to put this in our calculator, we'd do 50 NPR 4. And that will give us a big number, and it also doesn't ask us to evaluate that, so we'll just leave it at there. Okay, now 8 runners need to be assigned to their lanes for a race. How many ways can 8 runners be assigned to 8 lanes? Okay, well, we have 8 total runners, and we're choosing 8 lanes for those runners to go in. So we can put 8 NPR 8, or if we remember that rule, we can do 8 factorial as well. And if we put either of those in our calculator, we get 40,320. Okay, now how many unique ways can the letters in millionaire be arranged? Okay, well, if I count up all my letters, I have 11 letters, so I'll put 11 factorial. But now I have a couple that repeat, so I'm going to divide and count them up. Well, looking at I, we have 3 I's, so I'll do 3 factorial. And now if I look at L, I have 2 L's, so I'll do a 2 factorial. And if I put that in my calculator, I get 3,326,400. Okay, now how many different ways could 6 children sit around a merry-go-round? Okay, well, this is the example of a circle. So we're going to have our 6 people, but we're going to have to divide by that extra 6. And so our answer is going to be 120. You can do it that way, or you can do 6 minus 1 factorial, which is 5 factorial. Either way, you'll get 120 different ways to sit around the merry-go-round. Okay, now we're actually going to skip number 6 and move on to number 7. So in a running competition, a bronze, silver, and gold medal must be given to the top 3 girls and the top 3 boys. If 6 boys and 13 girls are competing, how many different ways could the 6 medals possibly be given out? So the trick to this one is to think about each permutation separately. So let's just think about the boys. I've got a total of 6 boys, so I'm going to start with 6. Okay, now I'm giving out 3 medals, so I'm going to do 6 NPR 3 as my first permutation. Okay, now for my second permutation, I'm going to think about the girls. Well, I've got 13 girls, and I'm still giving out 3 medals to them. And if I multiply those two together, I get 205,920. And that right there is going to be my final answer. Now don't forget to fill out this information about your pathway and how you could find the total number of outcomes for permutation in your pathway. There is some Delta math online that we're going to work on, and yeah.